Swayam Prabha. Digital India. Educated India.
So, hello everyone, today I will start a new module. It is the surface modification and characterization. So, in this module we will discuss different method to modify the surface, how to characterize the surfaces, and also we will see how these modified surfaces affects the biointerfacial interactions. So, first we will quickly summarize the module 6. So, there we discussed about the cell surface interactions. So, in the cell surface interactions, the first lecture we discuss what happens during the implantation of a biomaterials. So, there will be a surgery as well as the presence of a foreign material. So, these cause the host cell responses which are activated by the complement pathway. We discuss what are the different sequence of responses. Then in the next lecture we discuss different mechanisms of the cell adhesion which are mediated through the different receptor proteins. Then we discuss what are different cell adhesion molecules like integrin, cadherins, immunoglobulins. Followed by that we discuss the work of adhesion, or you can say the Gibbs free energy of adhesion, and how this adhesion can be tuned by tuning the surface energy of the solids. You can see the surface energy of the biomaterial surfaces. Then we briefly discuss experimentally how we can analyze the cell adhesion data, and then how those data can be fitted to the cell adhesion kinetics to determine the particularly initial rate of adhesion. Then in the last lecture we discuss how do we define the biocompatibility of biomaterials, then what are different in vitro and in vivo method to assess the biocompatibility of biomaterials. So, in today's lecture I will particularly focus on the surface modification, why we need to modify the surfaces, what is the purpose of surface modification, and we will discuss the few examples of the surface modification, like to control the bacterial adhesion, to regulate the protein adsorption, to regulate the cell adhesion. Followed by we will also discuss to regulate the corrosion or degradation of biomaterials. So, the first thing, as you know, the biomaterials have a wide range of applications, and these applications depends on the material property, what is its chemical composition, its morphology. Then we also go for different fabrication techniques, and followed by that these are the different intended applications, including the implant biomaterials for the tissue engineering, scaffolds, drug delivery and biosensor. So, apart from the biomedical applications, in the marine interface we see the biointerfacial interactions, in the food processing we see the biointerfacial interaction. So, in all these applications there is always a biointerfacial interactions which takes place between the outermost surface and the surrounding environment and if you are taking the implant, it is a body fluid. So, biointerfacial interactions, so it always takes place and which determine the, or you can say which regulate the fate of a particular material or a particular implant. So, as I told, particularly in case of biomaterial or implant, we see the material surface, this is your outermost surface, and this is the body fluid. So, there will be different interactions, surface water interaction, surface protein interaction, and the cell surface interactions. So, first will be the surface water interaction, followed by the protein surface interaction, then cell surface interaction. So, these interactions will take place, and all these interactions depends on the surface properties of the implant biomaterial. Apart from this interaction of protein and cells, because of various reasons, surgery or some infection, there is a biofilm formation, or you can say the attachment of bacteria as well, which is of course, this is undesirable, but we cannot stop it. So, these are the different biointerfacial interactions take place at the outermost surface of the implant biomaterials, and which decides ultimately the biocompatibility of a particular implant biomaterial. So, now as we know, these are different biointerfacial interactions which will take place with time once a body, or you can say a foreign body, foreign implant comes into contact with body fluid. Then why we need surface modification? Because as we know, a particular biomaterial is intended for different purpose, it has to interact with the biological system. So, we cannot avoid it, and now as we discussed, particularly the surfaces play a key role in the biointerfacial interactions rather than the bulk property. So, if you can tune the surface, we can tune the biointerfacial interactions, and these biointerfacial interactions determine the host response. In other way, you can say this decides the biocompatibility. So, you can say overall aim of surface modification is to tune the biointerfacial interactions for a intended application or to achieve the desired functions. So, that desired functions will depend on the type of application. So, for example, I have listed if you are having an implant biomaterial. So, the attachment of cells, mammalian cells is intended, it is desired, but at the same time bacterial attachment, or you can say the attachment of pathogens are undesired. So, this is just one example where we have to modify the surface in such a way to restrict or to promote the desired interactions, at the same time it should restrict the undesired interactions. Now, we can summarize what is the purpose of surface modifications. If you modify the surface, we are going to alter the surface property in order to enhance the performances in a biological environment. At the same time, it is important that the surface modifications should not affect the bulk property of the implant biomaterial. So, the surface modification should not interfere with the bulk property. At the same time, it should favorably tune the interaction with the biological environment to enhance its desired performances. Like as I told, one example was you want to increase the specificity towards a particular cell or towards a particular ligand to reduce the or to minimize the undesired interactions. So, these are the purposes or objectives of the surface modification. So, here you can say in the environment we may have both mammalian cells as well as the bacterial cell, but our interest is to restrict or inhibit the bacterial cell adhesion and to promote the mammalian cell adhesion, particularly if you are looking for the implant surface. So, starting from this, so now we can list the different objectives of surface modifications. So, I have listed a few here. So, to reduce the bacterial attachment, adhesion, or you can say the biofilm formation. To regulate the protein adsorption, because the protein adsorption regulate further the cell surface interactions. To regulate the cell adhesion, to prepare or design the anti-fouling or you can say the self cleaning surfaces, also to reduce the friction and wear, and to control or to impart the corrosion / degradation resistance. So, I have listed these few examples where we need to modify the surface to achieve these objectives. So, we will discuss one by one. So, first to reduce the bacterial adhesion or biofilm formation. So, as you know, this particularly this bacterial adhesion is a major problem in the biomaterial, because it lead to the lot of infections and even it may end up with the failure of the implant. So, we can say it is responsible for the biofouling. Now, bacteria is a cell, so its adhesion or its attachment occurs through the proteins and the polysaccharides which are there in the cell wall of the bacteria, but mostly it is a non-specific attachment, and also the composition of bacterial cell wall of the gram positive as well as the gram negative is different. So, there will be a different adhesion behavior of the gram positive as well as the gram negative bacteria. Also, the some surface receptors of particular bacteria, they also favors the different adhesive proteins like fibronectin, vitronectin, fibrinogen, and few bacterial species they have the pili on their, or you can say pilus on their outermost surfaces, they also facilitate the initial surface attachment. So, this is how the bacteria attach on the surface. Now, if you want to reduce or minimize this bacterial adhesion. So, we have to stop or we have to inhibit these interactions. So, traditional approaches or you can say the classical approaches is coating with the antimicrobial agents, like one example is the silver nanoparticles. If you coat on the surface, so it is expected it will kill the bacteria pathogens. Another example is to apply the antibiotics, and third example is to apply the cell wall disrupting agents, which are particularly in cationic in nature. So if we can have the antibacterial or antimicrobial agents, we can have the cell disrupting agents, we should be able to kill the bacteria when it comes closer or in contact with these antibiotics or antimicrobial agents which are present on the surface. But there is a limitation of these approaches. The first is when we are having these particularly these nanoparticles, or you can say these cell disrupting agents. So, there will be release of its components and sometimes they are toxic to the body. So, because of their release of course, there will be degradation with time of those surface coating agents, and they will release some of its components with time, and particularly for nanoparticles and this cell disrupting agents are found to be toxic to the body. So, which particularly restricts their use for the implant biomaterials or the particularly in vivo applications. Also, if you go for the antibiotics, so prolonged use of antibiotics, it develops the antibiotic resistance. So, these are the few demerits of these classical approaches to restrict the bacterial adhesion. So, we go for modifying or coating the surfaces with positively charged or surfaces with low surface energy or coating with the polymer brush. So, we will discuss each of them. So, basically positively charged surfaces result in electrostatic interaction between the bacteria and the surface, and if you are having the strong electrostatic interactions, so you have to tune the charge surface area in such a way that we achieve the strong electrostatic interactions which will restrict the cell growth and subsequent cell divisions. So, in that way it is going to inhibit the biofilm formation, or you can say the bacterial adhesion. So, typically when we go for these positively charged surfaces, so this adhesive electrostatic interactions, this is also affected by the ionic strength, particularly if you are talking about a culture media or a fluid system. So, it is going to have different salts. So, the presence of different salt system, it also affects, or you can say this weakens the electrostatic interactions. So, I have listed few examples like the processing of food, pharmaceuticals and cosmetic industries. So, wherever there is a interaction with the surface, so there will be the presence of particular fluid, and the fluid will have some salt solution which is going to adversely affect this strong electrostatic interaction between the bacterial cell and surface. Another thing is that few microorganisms produces some extracellular polymeric, and that polymer is going to again acts like a cushion, or you can say it is going to act in between the cell and surface. So, it is also going to interfere with the electrostatic interactions. So, in principle, if you are having a positive charge surface which can generate the strong electrostatic interactions, then it is going to inhibit the biofilm formation. But if you are going for this particularly in the real applications in biological systems, so we are going to have the some solvents or the, you can say, the buffer solutions which will have many salts. So, the ionic strength is going to affect the electrostatic interactions, and also few bacteria produce the extracellular polymers, and those polymers are going to act in between the surface and the bacteria, and which will ultimately interfere with the electrostatic interactions. So, next is the, if you can tune the surface free energy, or you can say the surface energy. So, as you remember in the last lecture during the cell surface interactions, we will discuss the spreading coefficient or the Gibbs free energy of the spreading or adhesion. It depends on the interfacial interactions. So, CS is the cell surface, Cl is the cell and liquid, and the Sl is the surface liquid, or you can say the solid liquid. So, for the favorable adhesion, delta G adhesion should be less than 0. So, as we discussed, it can be tuned by the gamma SL. If gamma SL value is higher, it means we are going to get the negative value of this, and it will facilitate. But at the same time, if you are decreasing the surface energy, so it is expected to decrease the Gibbs free energy of the adhesion. So, in this way, by tuning the surface energy of the solid surfaces or the implant surfaces, we can tune the spreading or adhesion. So, typically this low surface energy are the hydrophobic surfaces, but again in principle it works, but when we are going in a real biological systems, so in the presence of the particularly the hydrophobic surfaces, it is going to induce the hydrophobic interactions, and that hydrophobic interactions may attract the surface active polymers or some other components like some salts or some other macromolecules. So, ultimately the surface property is going to change after the adhesion of this other undesired interactions, like a interaction of the components or the surface active proteins or surface active polymers. So, basically when we go for the interaction in the biological systems, so apart from the cell surface bacterial surface interactions, the other interactions affects the whole process, and which makes this process or the bacteria surface interaction even more complicated or more complex. But theoretically, if you can lower the solid liquid interfacial tension, then we are going to decrease or lower the spreading, and in that way we can inhibit or minimize the bacterial adhesion. So, another aspect is if you can graft the soluble polymers like a polyethylene oxide, which at the one end on the surface and other end will be in the solution, which is going to interact with the bacterial cells, and depending on this chemistry, as we know, there will be different intermolecular interactions, starting from the van der Waals interactions, this electrostatic interactions. So, it may include both attractive as well as the repulsive interaction, depending on this conformation as well as the chemistry of this polymer brushes. And if you just see in this picture, the polymer brushes occupy the two different conformations. One is the mushroom and other is the brush conformations. So, particularly these polymeric brushes are desired for this antibacterial coating, and depending on this, if you just see the distance between this D, let us say this D distance between the two molecules or two polymer chains, it is going to regulate its conformation. If distance is higher than the size of molecules, it is going to form the mushroom conformation. If distance is less, then polymers will be in the brush conformation, or you can say the elongated conformation. So, you can say this mushroom or brush conformation depends on the grafting density. And this grafting density is going to affect the, let us say I am plotting the inverse of 1 upon grafting density versus adhesion So, there will be let us say some value here. So, this was the adhesion before the grafting. Now, if you go for the grafting, then we can minimize it as well as we can also improve the adhesion. So, it will look like this, and it will go like this. So, depending on the grafting density, you can tune the surface excess or the adhesion, or you can say the adsorption. So, let us say if this was the point, the surface excess in the absence of grafting. So, when we grafted more, so here we have minimized 1 upon grafting density, means here we are having the maximum grafting. At that case, the adhesion is minimized, but at the same time, if you go further here in this region, so this adhesion is higher than that without grafting. So, we can say this, of course, grafting density is going to affect the adhesion, or you can just say the surface coverage is going to regulate the adhesion, but it can regulate in the dual manner. It can, depending on it can increase as well as the decrease, but here we are more interested in the minimizing the adhesion. but if you look for the cell surface interactions, particularly mammalian cell surface interaction, then you will be interested in the maximizing the adhesion. So, anyway, that we will discuss in the next slides. So, here the deposition of the cell, it decreases with increase in the grafting density. So, depending on the grafting density of that polymer brushes, we can tune the bacterial adhesion or biofilm formation. So, now we will go to the regulate the protein adsorption. So, specifically for the this protein adsorption and cell adsorption, cell adhesion. So, these two will look at very briefly, because we have discussed that this surface protein interaction and cell surface interaction in this modules 4 to 6 we have already discussed. So, here we will quickly go through the protein adsorption regulates the cell surface interactions or the cellular attachment, and which particularly depends on the what is the amount of protein amounts of protein and the conformations. So, conformation means change in the secondary structure. So, if protein have lost its conformations, means its intended function is the lost. In that case, the desired cell surface interactions will not take place, and it may lead to the biofouling and the failure of the implant. So, the objective is to promote the cellular attachment and to reduce the undesirable or uncontrolled responses to implants or other biomedical devices. So, particularly if you are looking for the implant, so it should promote the cell attachment, but at the same time if you are going, let us say, other biomedical devices like a biosensor. So, it should be specific to the particular ligand or particular, let us say, protein molecules. In that case, the surface should be very specific and it should avoid the any non-specific adsorption. So, if you go for the surface modification, the first objective is to reduce the non-specific adsorption. So, different polymers, we starting from the hydrated and hydrophilic polymer like polyethylene oxide is very well known to reduce the protein adsorption, because of its spatial arrangement, which forms a hydrated water layer between the surface and protein. Apart from that, the coating of various polymers, ceramics, self-assembled monolayers and other bio macromolecules have been tested to tune the or regulate the protein adsorption. Now, if you want to regulate the cell adhesion, so here we are particularly focusing on the mammalian cells. So, depending on the application of a biomaterial, as I told, if it is a implant, it should promote the cell adhesion, but if it is a biosensor, it should be specific and it is desired that there should be almost no cell adhesion. So, like I listed here, in the bone implant, osteoblast cells need to integrate with the implant, so that it can grow, it can proliferate and it can differentiate to form a particular tissue. Now, but if you talk about the sutures and the pacemakers, then our objective is there should be no cell adhesion. So, these are the two contrast examples. In one case bone implant we need the osteoblast cell to adhere or integrate, but in case of sutures and pacemakers we are avoiding where that cell adhesion should be limited. So, the whole idea is depending on a particular biomaterial we should look to prepare the biomimetic surfaces to tune or to achieve the desired interactions as happens in case of natural systems. So, particularly natural system means I can give two examples. One is the lotus effect. So, where we see because of this surface topography it is like a self cleaning surface. Also in the lizard feet if you just see this nanostructure surfaces which gives the maximum adhesion strength so that it can climb on the vertical wall. So, particularly if you look for the bone surface, so in the bone surfaces it promotes the attachment of the particular tissue, but at the same time it avoids the blood clotting or you can say the biofouling. So, these are the way for a intended applications we prepare the biomimetic surfaces. So, here both for the protein adsorption and the cell adhesion hydrophilic surfaces resist the protein adsorption or they minimizes the protein adsorption. Hydrophobic surfaces they favors the protein adsorption, but these two cases again depends on the what is the hydrophobicity of protein. City of proteins. So, depending on that the hydrophobicity of surface regulates the protein adsorption. Also, if you are particularly looking for the blood contacting surfaces, so we can coat with the anti thrombogenic agents like a heparin to avoid the blood clotting. So, if you want to resist the platelet adhesion we can coat with the or you can pre-adsorb the surfaces with the non-adhesive protein. So, albumin is a you can say non-adhesive protein. But if you want to promote the cell adhesion you can go with the fibronectin or the collagen. So, these are the adhesive proteins, means they promote the cell surface interaction, particularly this fibronectin and collagen they have this RGD peptide sequence which integrates with the integrin and facilitate the cell signaling, so that cell can interact on the surface, they can grow and then they can proliferate, differentiate on the surface. Also especially for the bone cell as hydroxyapatite is the biosimilar material which have very close composition, particularly this Ca by P ratio 1.67, it is very close to that of bone. So, it promotes the bone cell adhesion. So, accordingly we can choose which type of surface modification we are looking for. Now, next we will discuss about the anti-fouling or the self cleaning surfaces, as I talked about the lotus effect. So, if you are having highly super hydrophilic surface or super hydrophobic surface, so in case of super hydrophilic surface there will be the water layer between the particle and this is a water layer. So, it is going to completely wet. So, it will remove the contaminants. In case of super hydrophobic surface, there will be the formation of complete sphere, means it is not going to wet. So, water molecules can flow from the surface without wetting. So, there will be no wetting here, and water will form a particular drop, or you can say particular sphere. So, that the contaminant can be absorbed into the water and it can be removed. So, particularly for removing of oil, grease, other particulates or some biological contaminants, this anti-fouling or self-cleaning surfaces are prepared. One example is we use the non-wetting cloths for different biomedical as well as let us say for the raincoat. So, there will be no wetting as well as these surfaces have the self cleaning property. Apart from that, especially for the joints, we need to reduce the friction and the wear. So, we require the high lubricity, particularly at the bone and joint implant, to reduce the friction and wear, because in presence of friction and wear, the intended functions are we see the joint pain, joint replacement. So, these things take place. So, particularly this hydrophilic modification increases the liquid or the hydrophilic materials on the surface, like synovial fluid. So, one option is to go for the modifying the outermost surface with the hydrophobic coatings. Apart from that, different polymers, hydrogels or the proteins are also used for the coating to minimize or reduce the friction and wear between the joints. So, particularly for the in vivo applications, the lubricant surfaces tend to exert low stress on the surrounding tissue, so that there should be no inflammatory responses. So, these are the different way how we can minimize, particularly for the joint or the bone implant. To minimize, our objective is to reduce the wear and the friction. And the last one we will discuss about the corrosion and degradation resistance. So, particularly if you are going for the bioresorbable materials, especially for the let us say magnesium alloys. So, for the magnesium alloys, they are bioresorbable or you can say biodegradable materials, but at the same time their rate of degradation should match with the rate of tissue formation. So, because of this mismatch, we have to regulate its degradation or corrosion behavior. Apart from that, there are other materials which get corroded, particularly in the biological environment. So, this higher rate of degradation, it may start the immune response. Finally, it may lead to the failure of the implant. So, we have to go for surface modification to regulate, or you can say control the corrosion or the degradation. So, particularly we add some inert layer. So, that inert layer minimizes, or you can say it interferes the contact of the surrounding environment with the outermost surface to retard or to slow down the rate of degradation or the corrosion. So, here the surface functionalization we are aiming to add the degradation or corrosion resistance. So, different way is to tune the surface chemistry, what is the composition of the biomaterials. you can tune the wettability, we can make the highly hydrophilic or hydrophobic surface. So, if it is hydrophobic, it is expected it will not get wetted. So, it may improve the corrosion or degradation resistance. Also sometimes difference in the Young's modulus of the surface and coating. Whatever we are coating, if there is a difference, so we do not get the desired adhesion of the surface and coating. In that case also it may affect the corrosion behavior. So, whenever we are going for the coating material and surface should have similar mechanical properties. Also the coating thickness, because with time it is going to degrade. So, here if you just see with increase in the thickness, there is a decrease in the weight loss or the mass loss. So, particularly for magnesium alloy, it is reported or it is found that coating thickness should be greater than 1 micrometer to achieve the desired degradation behavior. And apart from the coating, what is the final finishing of the material which lead to the formation of local pores which penetrate throughout the coating and the surface. So, these are the few aspects particularly related to the degradation or corrosion behavior of the surfaces. So, here I conclude this lecture. So, we discussed why we need the surface modification, what is the objective of surface modification, its purpose of surface modification. Then we discussed few objectives starting from the to avoid the biofilm formation, followed by that we discuss to regulate the protein adsorption, to regulate the cell attachment, to prepare the anti-fouling or self cleaning surfaces, to reduce the wear or friction, and to regulate or control the degradation or corrosion behavior. Thank you.